Hello friends, welcome to our channel Knowledge Amplifier. So today in this particular video, I am going to explore data compaction, one very important concept related to the performance improvement in your big data pipeline, and especially if the source of your data is some sort of real-time streaming platform, then data compaction can surely help to improve the performance of your data pipeline. So what is it? What problem basically it solves? And then the practical implementation of data compaction. All these things we are going to cover today in this particular video. Okay, so without any further delay, let us directly jump into the theoretical understanding part first. So in most of the organizations, we are having some sort of mobile app or website. So those applications from devices generate different kind of real-time logs. If it is website clickstream data, that can be called as web access logs. Then if it is mobile app, then mobile application logs also generates in near real time. And if it is some sort of sensor, then IoT device logs also get captured almost in near real time. And then we generally publish this kind of real time streaming data in Kafka or Amazon Kinesis. From there, using Kafka Connect or Kinesis Firehose, we flush or dump the data in our data lake, which is often AWS S3. Okay, so we can say continuously and periodically using Kafka Connect or Kinesis Firehose, this kind of streaming data get flushed in our S3 location. And when I'm saying periodically, the period is a very short period. Otherwise, it will be termed as a batch processing. We need real-time processing, right? So it is continuous, and the period for which it basically buffer or accumulate the data, that period is not a very long period. It is a short period. In terms of seconds to minutes, we generally configure in our Kinesis Firehose flush interval, or in our Kafka Connect flush interval also we can configure this. Okay, and although before flushing we implement the buffering in Kafka Connect or Firehose, but whenever the files get written in our S3, because the period is very short, whatever files are written in our S3 location, they become very small files in the size of few KBs, right? So I hope you understood up to this. Whenever our streaming platform dump the data in S3 location, that often have small size in terms of few KBs. Okay. Now suppose you created a analytical layer on top of your S3 landing zone. Maybe you are querying using Athena, or from Snowflake external table you are querying the data. Now obviously, because that particular analytical engine need to scan lot of small files, it need to first list all those files and then open individual files and then read the content. So obviously, I hope you can easily understand that it will take more query time, and obviously it will return into decrease in performance in our analytical workloads. And this is nothing but popularly known as small file issue in our big data world, right? So same goes for pyspark also. If suppose you are reading some data from some S3 location where multiple small files are there, then whenever you try to do some big data processing using pyspark by reading those data from S3, obviously it is going to take a lot of time, because that network bandwidth will be consumed by a huge amount. It need to scan all the files, list all the files, read the content by individually opening the files. So this will take some time, right? So somehow if we able to aggregate these small files into large batches of files, that will improve the efficiency of our big data workloads, and that is nothing but data compaction. Okay, so I hope the fundamental problem what data compaction solve, that is clear to you. So what is written here, that compaction, as I told you, it is nothing but merging small files into large ones, right? Now suppose you have 20 small files of 2 KB each. Instead of that, if you create a single file which contain the same data by accumulating those small files, obviously it will be having maybe some MB volume. And on top of that, if you run your PySpark workloads, that time the pipeline efficiency will be better. So that's what the data compaction does. Basically, we will try to merge small files into large ones, right? Now the question is how to merge all these small files into large size of files. That we need to explore so that we can implement that same mechanism in our data pipeline to solve this particular problem, right? Now, as a straightforward solution, we might think that we will read the content where all the small files are available, that S3 location we will read in PySpark, and then we will apply queries property of PySpark to decrease the number of partitions in our data frame, and then the transformed data we will write in another S3 location where big files will be available, right? That way we can think, and ultimately that's what we are going to implement. But the problem in queries is you can only mention how many partitions you want. Okay, that is, suppose you are having 20 small files, Spark will read that in a data frame and you apply queries. If you mention queries 5, then in the output directory 5 large files will be written. If you mention queries 2, then 2 large files will be written. But using queries, you cannot control the output file size, whatever we are writing in output directory. Okay. In fact, not only queries, currently there is no option to specify output file size in Spark while writing the data. But ultimately we want to make that. We want to merge small files. Maybe if it is in few KBs, we want to merge them and we want to make some large files, but the large file size should not be anything. We can keep the value as predefined one. Maybe individual file size should be, for example, 2 MB. Okay, so if in our input directory we are having files of KB size volume, what we will do? We will merge them and then we will write that data in that MB format, whether it is 2 MB, 3 MB, predefined value. Based on that, we will write that data. That kind of mechanism we need to implement. So how we can do that? So to do that, we are having a 3-step process. First, what we will do? We will scan our input directory where small files are written, which is written using Kinesis Firehose or Kafka Connect. What we will do? We will basically calculate total number of files available and total size of our input files. Okay, so in our landing directory, what is the total size if we accumulate the size of individual small files? What is the total size we will get? That we will compute, and number of files. How many total small files are available in our input directory? That we will calculate. And then we will calculate average file size in our input directory where our small files are written. And how we can compute average file size? It is very simple. Total size divided by total number of files, whatever we computed in our step 1. Okay. And already we will be having a predefined value of desired file size in the output directory. Maybe for example 2 MB, 3 MB, etc. And these should be individual file size. But if our average file size in our input directory is less than desired file size, that means there is small file issue, right? And that time we need to apply queries. Now in queries we need to mention how many files we want to get in the output directory, how many large files we want to get after merging the small files, and what is the value for queries. How we can compute that? It is very simple. Ideal number of partition for our output directory is total size, whatever we are having in our input directory, divided by desired file size, what we are expecting in our output directory, right? Because total number of files multiplied by individual file size is nothing but total size, and total size in input directory and output directory will be same anyway, right? Because we are just merging these small files and making large files in the output directory. We are not filtering data or removing some data out of it, right? So total size will be same in input and output directory. And in the output directory, for individual size, what is the desired value? That is pre-configured. So all we need to know, how many files Spark has to write. That we can easily calculate using this particular formula, right? So that's our algorithm, what we can implement to achieve data compaction to avoid small file issue in our S3 data lake. Now, without any further delay, we will jump into the implementation section. So here, if you see, we are having a S3 directory where we are having a lot of small files. California housing train data. It is a very popular machine learning use case. And I have just read that CSV file and I have written a simple script to split that bigger chunk of data into small CSV files. And you can see each file is having 2.1 KB volume. So if I go to the next page or next page, here you can understand that all are small files, right? Now what we want to do, we want to implement data compaction for our this particular directory, and we want to write that processed data or compacted data, we can say, in another directory, and let's consider that as large data set. That is another folder what our Spark will be creating. And then what we will do, we will basically create a Athena table pointing to our this directory where small files are available, and we will be creating another Athena table pointing to our large dataset output directory where compacted data will be stored. And then we will see by running some query which Athena table is performing better, whether with small files it is running first or whether with compacted data it is running first. Okay, so that we will try to inspect. That way we will able to understand that whether data compaction really improving the analytical workloads in our data pipeline or not. Okay, So for that, here I have written a code that let me explain first. So first what we are doing, we are reading the data from our input directory where small files are available. So I will just run this code. So here you can see the read operation is completed and elapsed time is 0.14 second. Okay. Now we will apply a very simple operation on our input directory, that is df.count. I will run this and let's see what output it gives. And it took 0.12 second and the output is 17,000. Okay. Now we will apply data compaction on this data using Python. So first for that I am importing some necessary modules and I am creating S3 session. So I will run this, and now here we have written a simple function. What this function will do, it will basically go to our input directory and then it will calculate two things. One is number of files available in our input directory and the total size of our input files or small files we can see, right? So what it is doing, so first I am defining one empty list called keys, and here I am creating S3 paginator, because here if you see in our input directory we are having multiple pages, so it should not just scan partial data. To scan whole data we are implementing paginator, and then here we are storing all those paginated output in this particular keys array whatever we have created, right? And then here we are iterating in that keys array. We are extracting the file size of individual files, and that we are adding in partition size in bytes, what we have defined here as 0. So ultimately once the for loop is executed completely, in the partition size in bytes in this particular variable, total size of our small files from input directory will be available, that is accumulated volume of all these small files, right? And partition file number plus equal to 1. So once the for loop is executed, in this particular variable how many small files are there in our input directory, that count will be stored, and we are returning both variables. So I will run this particular code. So yep, it is done. And now here we are defining the input bucket and the prefix where our small files are available. If you see the directory where small files are available, that is multiple small dataset, that is what we have given, and desired size in bytes we have configured this particular value. So what is this? Let us try to calculate once. So this is nothing but divide by 1024 if we do, that is nothing but 300. Okay, so we are giving such input to our code which will make sure after data compaction in the output directory individual file size should be nearly 300 KB, right? That's what this code is saying. So I will just run this particular one, and then here we are applying data compaction. What we are doing, first we are calling get partition num and size. This will basically give me total size in our input directory and the number of files available, and then we are calculating average size of individual small files, and then optimal file number. As I told you, this is the formula, that partition size in bytes divided by desired size in bytes. So that optimal file number we are computing, and if average file size in bytes in our input directory is lesser than desired size in bytes, which is basically configured here, that means it is having small file issue. So we are reading the content from our input directory, we are repartitioning, and the value we are passing as optimal file num, this particular value. Okay, it will make sure that in our output directory the individual files should be having the size of nearly 300 KB, and then we are writing in overwrite manner format CSV option header true, and this is our output directory. Okay, so this is our function. So I'll just execute that, and then I can execute the compaction function. And let's see here, as of now the large dataset folder is not there. If I refresh, still it is not created. Let's wait for a few seconds. Here the code is running, and here calculation completed, optimal file number 5. So here if I refresh, here you can see recently large dataset folder got created, and if I expand that, here you can see that the files from input directory are compacted and written to nearly 300 KB volume, right? So although in pyspark we are not having the functionality to directly control the size of output files in the output directory, but we can compute in this manner and we can easily control the value. Okay, and now here what I will do, I will basically read that compacted data from large data set, and then we will apply df2.count on it. Okay. Because this is not a very big data set, so we might not able to see a large difference. But if your data lake is very huge and if there are a lot of small files are available, then after log compaction, surely you will see the improvement in the analytical engines. Okay. So here data read is complete from our output directly after data compaction, and I will just run this df2.count on our compacted data. So here you can see it returned the same result as of our input value, that is 17,000. So due to compaction, here one thing it is clear that data is not at all get changed. Instead of small files, we are merging to some large files and writing it. And if you now compare the performance for reading all the small files from the input directory, it took 0.14 second. And for our compacted data, it took 0.08 second. So obviously with respect to reading, here we can clearly see the improvement. And when we are applying df2.count in our small files, we were getting the outcome in 0.12 second. And when we have implemented that same in our compacted data, we are getting the result in 0.08 second. Okay, right? So that's the beauty of log compaction. Whatever operations we are doing on the compacted data, here we can see improvement with respect to our small file workloads. Okay, right? And now here, if you think that this file size is also small, if you want to make a single file out of it, which is having some sort of MB volume, that also we can do. All we need to do is basically tune this particular parameter. So let me just change this value and show you. So here I have given another high value now. And if you check this particular value in KB, this divided by 1024, this is basically 1667 KB. And if you again divide by 1024, it is nothing but 1.6 MB nearly. And actually our data set, what we were actually having, that California housing trend data, that itself was having nearly 1.7 MB volume. So we can assume that if we apply this particular high value, then obviously in the output directory, we should be getting kind of a single file which contain all the data. So let's apply that particular compaction now. So here this is executing. Then we will apply compaction, and then here I will run the compaction. And now currently we are having 5 files in the output directory, but soon we should see a single file of nearly 1.6 MB volume. And whether it is single file or multiple files, that we no need to worry. Spark will automatically compute that optimal number of files, and that it will apply in repartition, right? So here you can see optimal file number 1, as I told you, it will be showing. And here if I refresh, currently we are having only 1 file. And we can always read this particular data, and we can apply df.count on it. Let's see whether any performance change or not. So here the data read operation was completed in 0.08 second, where for uncompacted data it took 0.14 second, and for df2.count for the compacted data, the count operation took 0.08 second, and for uncompacted data it took 0.12 second, right? So always by applying compaction we can see an improvement. Now let's try to observe the same in Athena, whether for data analyst team who are basically using Athena for their ad hoc analytics purpose, they can face some improvement in query performance due to this data compaction or not. That we'll try to explore. Okay, so for that, first I will be dropping some tables just to clean up my environment, and I'll be creating a database hello world where I'll be creating 2 tables. One will point to that uncompacted data, another will be pointing to that compacted data. Okay, so here if you see this particular small file data table I am creating, pointing to our input directory and multiple small data set. Basically this directory where our small files are available. To that particular location, we are creating one external table with small file data. Okay, and then here we can apply select count star on this particular data, and here we are getting 17,000 as usual, whatever we got in Spark. And this is the time in queue, this is the runtime, this is the data scan. So this information I'll have a store here. And now what I'll do, I'll be creating another table pointing to our compacted data. So if you see for this external table, the bucket is same, but the directory is large data set, which is basically having our compacted data. Okay, So here I will just create this particular table. Anyway, it is having that same schema and all. And now we will apply select count start image. Let's see. So here, this is the statistics for our compacted data. Now we will compare our uncompacted data and compacted data side by side. So all I will do, so this is our uncompacted statistics and this is our compacted statistics. Time in queue anyway you can ignore because that is queue time, we cannot consider that. Runtime for the uncompacted data, it is 1.27 seconds for count start. Whereas for our compacted data, it is only 494 milliseconds, right? And data scan for uncompacted data, it is 1.72 MB, whereas for our compacted data, it is 1.63 MB. Obviously, you can think this way that for uncompacted data, Athena might need to list all the files and go to individual files, open those files. So maybe data scanning is increased for that reason. But ultimately, due to compaction, there is no data change. And that I can show you using this particular query, that we can basically try to find out the difference between large file data and small file data. And then here, small file data versus large file data, and that union we can take. If these two data set is having same data, then ideally this will result into 0 value. So here some network issue I am facing, just let me check, and let me just try to execute this query again. So ideally this should give 0 as outcome, which will make sure that large and small file data is having same data actually. And see, it is giving 0 in the result set. So that is indicating that using this data compaction, all we are doing, we are merging small files into large files so that our analytical workloads performance will be improved, right? That's all. But data wise, there is no change. I hope you understood this. This is all for this video. All the codes and the documentation link I'll be sharing in the description box. Just go through that. It will help you to understand this concept in a better way. If you find this video helpful, then please like, share and comment. Subscribe our channel if you have not subscribed till now. And don't forget to press the bell icon to get the notification of our latest videos. Thank you for watching.